Good morning, good evening, good afternoon. Hope everyone is well. I'm here. I have an annoying headache, but we're going to push through it because I love you all. So annoying. I hate headaches. They suck. Anyways, enough about me. How you find people today? What's up, Impish? Good to see you. Hope you're starting to feel better. Greedy. Good to see you, buddy. Sleazy. What's up, bud? Mystic. Good to see you. Dance. No worries, brother. No worries. You took me down a rabbit hole, so I'm much more in depth than I thought I would be, so it's taking more time. Linda, good to see you. Belandris, what's up, buddy? I don't know why you're conscious. Man Bud, hello. Yeah, I'm staying here. I'm staying here. Over on Rumble, we have some people watching. Go ahead and say hi. I'll love you for it. Hit that thumbs up, plusy, whatever they call it nowadays. All right, so we have one of the fiercest debates in science that we're just starting to unravel what's going on with it. It is wave theory. So it's wave, and we'll go into both the wave theory and the particle theory of light. We're talking specifically about light. Let me get the book. Could have had that. That one. I skipped universal. No, we did. I think we did. I have to look back. I think I skipped one, but that's okay. We can do wave theory this week. So our book, our 30-second theory. You only have to go to the beach and be hit by a wave to appreciate the waves carry energy. But they do so in surprisingly diverse ways. Some waves, such as sea waves and sound waves, physically move particles of water or air, or whatever medium they're traveling through. These waves can come in two types. A sound wave is longitudinal and creates vibrations that move the air parallel to the direction in which the wave is moving. Transverse waves, such as electromagnetic waves, oscillate in a direction perpendicular to the direction of travel. Polaroid sunglasses work because they block out transverse oscillations moving up and down in a certain orientation. For example, up and down light waves oscillating in another direction from side to side, for example, pass through unaffected. If the light was a longitudinal wave, Polaroid lenses would have no effect at all. Most wave theory was worked out in the 19th century when pioneers such as Thomas Young showed how waves can be manipulated. Waves are reflected by certain materials, refracted as they cross the boundary between two media, or diffracted, which means they spread out as they pass through a narrow opening. They can also interfere with each other, canceling each other out completely. In some regions of the medium while combining it into larger, more powerful waves in other areas. And so there are different wave processes for sound waves. There are physical waves, all that kind of stuff. We are going to, Mr. Meg, I made a whole PowerPoint today. There's a test. There's a video. Yep. I'm on today. Related theories is electromagnetism and quantum field theory. Waves are everywhere in the ocean, the air, or even in the vacuum of space. Wherever they are, all waves have a wavelength, the distance from the start of one wave cycle to the start of the next. 3-second thrash, the reason why in space no one can hear you scream. With the discovery of quantum theory came the realization that electromagnetic waves are really the movement of packets of energy called photons. Albert Einstein won a Nobel Prize for this discovery. Before then, light was thought to be a series of waves oscillating at different frequencies. The energy held by photon relates to the frequency of the light wave's oscillation. The energy also relates to the color we see. Blue light is comprised of higher energy photons or faster oscillating waves than red light. So, to tangent for a minute, that's how we can tell, for example, that something's red shifting by the wavelength and the energy. It's okay, Sleazy. It's all fun, buddy. So like I said, wave theory can go into a lot of different things. I specifically chose the portion of it that has to do with electromagnetism and light waves and particles and that debate because I think it's very interesting and I know the most about it. So, wave theory. So these are some of the key people that contributed to wave theory. You have Planck, Huygens, and Newton. We've seen Newton a couple times. He's pretty influential in the beginning of science. Actually, I can make this big because who cares about me, right? So, like I said, one of the biggest debates is particle or wave. Also, I can bring in the double slit experiment here, so that works. Can wave theory explain why water bubble? Actually, it probably could, because the waves were synced to the way that relaxed your body to make you sleep. So you could probably. So this is electromagnetic wave propagation on your right. And the other is just an illustration. So this is different oscillations through space that show wave theory. Here's some quick facts. Why is the whole thing not on there? Oh, you suck. So apparently StreamYard is not the same size as the PowerPoint is. So that's beautiful. So light has a definite speed. The speed of light can never change on its own. I disagree perfectly with that. It can change based on media. It can change based on several other factors. It is not as constant as we believed it to be. And we can prove that with technology that we now have. So a single beam of light can travel around the Earth 7.5 times in 1 second. So it's not realistic to think it's going to, because that would be inefficient and it'd be going far too fast, and it would shoot off into space. But that's just a reasonable explanation of the distance that it can travel in 1 second. That's how fast light speed is around the entire world, 7.5 times 1 second. Like almost all other electromagnetic waves, light waves also travel with a speed of 300,000 meters per second. So a light year is the distance that light travels in 1 year. It's kind of a weird concept, but yeah, that's just a way that we can bring down the values, because if not, it's such a big number that we can't grasp those kind of numbers and we can't make sense of them. So let's see. Let's do the math. So that's 9 trillion. That's how many meters that it can go in 1 year. So linear acceleration, proton shit, can't remember, nuclear fusion. Sure. If this was a night show, I'd have a quippy comeback, but I will reserve. To deal with light waves, we need to consider a sine waveform. Brightness, or we can say the intensity of light, is represented by the amplitude and depends on the distance and how much the light source produces. We can agree on that. And it comes down to how many particles are actually being sent out. No, you're totally fine. So like I've said many times, you go to the beach and light that hits you in the eye is a particle that has traveled billions of miles over billions of years, and fantastic. I'll be ready. Billions. Isn't that the same as the fine they gave? Yeah. That whole thing's crazy, but so it comes from so far away. The light emitted from a source is measured in lumens. That's just another measurement that we can use. The wavelength of light is way shorter than infrared waves. And that's an interesting thing that I'm sure everybody knows, but our I should have put that in there, but the spectrum of light that we can actually see is mind-blowingly small. We're not very efficient at it. We're good at what we do, but overall we don't see very much light. It's kind of crazy. So this is visible light, and this is the wavelength. And this is the little sliver of visible light that we can actually see. And this is just a sign of the wavelength. So your gamma rays, X-rays, UV light, infrared light, and even radio waves are all on this spectrum. And we can see this little teeny sliver. So, yes, mercies for the weak. Don't treat me any differently. Jerks. As per the formula devised by Planck, the energy of a photon is directly proportional to the frequency of light, given as E equals hf, where h is the Planck constant of 6.63 times 10 to the negative 34 joules per second. This guy, this is an attractive gentleman. Belandris and I last night were talking about, well, I was talking and Belandris was listening, about how insanely attractive the people of the science past were. So Christian Huygens, the wave theory of light was the way that scientists understood light. The theory was first spread by Christian Huygens and Robert Hooke in the 17th century. So we're talking about way back where we didn't have any of the modern technology. What's up, Vicky? And it's pretty amazing that they established some very fundamental and concrete beliefs on their scientific system without having anything, really. They at the time predicted that light was a wave, as it could refract or bend when traveling from one medium to another, reflect off shiny surfaces, diffract around objects, etc. Observers can also see an interference where troughs and peaks of waves add up to produce brighter light or cancel out to create darker regions. However, in the late 17th century, many scientists were confused about the fundamental nature of light. They were entangled in a debate whether the light was a wave or a particle. And we still are up until very recently. So now we're going to watch a video from Slow-Mo Guys. I played clips of it before, but we're going to watch it all the way through. So,
camera that absolutely blows my mind. Now, we've filmed at some very high frame rates. We're talking up to about half a...
Northern Lights are my... I have tried so hard to see the Northern Lights. I have driven hours up north when they increased solar activity. We went to Alaska to try and see them. So many different things, and I just have not caught them yet. I would love to. I'll have my camera ready, but I have not caught them yet. So if anybody's seen them, I hear they're mystifying. And we're in a solar minimum, so we should be able to. And there's issue with our magnetic field, so we should start seeing more of them.
Million, which is
not to be sniffed at.
Serious frame rates. Their camera puts ours to shame and does 10 trillion frames per second.
That's 13 zeros. For reference, that is 20 million times faster than the fastest we've ever filmed on this channel.
And there's not much you can't film with 500,000 frames a second, but one of those things is the speed of light.
Not a bad subject.
No.
Let's get in there.
All right.
Yeah, I agree. And yeah, Earthcam, but I want to see them, like, I want to feel them. I want to see them in real life.
Even the shoe cover technology is cool.
I kind of want one of these at home, actually. Yeah. Just for people.
All right, let's go in, see what this cup is all about.
Nice to meet you.
Nice to see you.
How's it going?
Good.
So, what are we doing here?
I'm just going to leave his name up there. I can make a joke. Partially because I have to stop the video. Partially because I think it's funny.
It looks all very complicated.
This is the world's fastest camera.
Oh, okay. Yeah, it's the world's fastest camera. So, there you go. Just as easy as that.
How big is the actual camera part?
I can show you. That big box is the camera itself, and here is the optics that we designed to make the thing work.
Very cool. So a lot of the times in our YouTube comments, we get asked to film the speed of light. And I have to always reply to people, letting them know that the speed of light is almost incomprehensibly fast. And even our cameras under 1 million frames a second will never see anything like that. Is this camera capable of filming the speed of light?
Yeah, that's basically what we're gonna see. For the example I'm going to
So a camera that's so fast. Well, you know, if you're giant, then this world's not made for you. Unless you're on my ship. Then it is. Bro, those guys really, really upset me last night.
show the light will move about the length of this bottle.
In time, how long does it take for light to start here and end here?
It takes about 2,000 trickle-second.
It's pretty quick.
Pretty quick.
Yeah.
So for the audience, it goes milliseconds, microseconds,
Is it nanoseconds?
nanoseconds, picoseconds, femtoseconds.
Yes.
So we're on the sort of pico-femto scale.
So that's how many zeros before the... What's up, Leanie? That many zeros.
Yeah.
Stuff.
Yeah.
We've never done that before,
So
for sure.
very
Yeah,
quick.
no, this is completely on another level. So shall we set up the first experiment?
Sure. Yeah.
Start with the bottle?
Yeah. Everyone should wear laser goggles.
Okay.
We have some.
Do I look good?
You've got like side panels in
You
your
look like you're
glasses.
about
You
to-
look badass.
It looks like you're about to go skiing with a welding torch. So I assume because we're trying to film...
These guys are funny to watch too. They're called slow-mo guys, and they're incredibly British, annoyingly British, but they're good guys. It is, and it's so hard to wrap your head around it. What's up, Just Dawn? Like a lot of these concepts, we can't even like you can't even put them into your brain because it hurts. That's about the correct. Yeah. It's very, very quick.
Light, it'll be useful to turn all the lights off in here, right?
Yes.
Otherwise we'll just get...
Yeah. You get a lot of ambient light coming.
Right.
Yeah.
Okay. Let's get ready for lights off.
Can you hold this, please?
I'll hold this.
Yeah. Thank you.
These guys, we're playing this Sea of Thieves still, and it's like a pirate game or whatever. And they stole our treasure, messed up our quest, and we tried to sink them, and it was this big to-do. We finally sank them and killed them. Unalived them. Forgot we're on YouTube. But they were really being jerks about it, so I was not very happy about it last night.
I'm excited. I get giddy by this frame rate stuff.
We want to see the light propagation from the side, so we need to make sure that the light is scattered out of the plane. If you put the milk molecules inside, then you can see light scattered from the side.
So this is a bottle full of water with a bit of milk in.
So I'm going to turn on the laser.
So all you do is just move mirrors and lenses around, and then it goes to different areas.
Instead of move the laser, the laser is too big. See, the light hits the bottom of the bottle, so it goes through the bottle.
Is it a powerful laser?
It's very powerful. It can basically burn any like papers.
I will stay away from that.
Yeah.
You can see it glows.
That's cool.
So the first
That's
thing
so cool.
I'm going to capture is just static image as our reference. For today,
So that's the bottle. That's the static image of the laser coming through. Yeah, and that was just so unnatural. Like, there's no way. Like, I'm not saying they were cheating, but it was so unnatural to be underwater and perfect shotting like that was insane. What's up, Aaron? What's up, Bobby?
going to try 100 video per second.
Excellent. I mean, I remember when I was excited.
100 billion frames a second. It is taking 100 billion images in 1 second.
And when we started shooting, we moved from 1,000 frames a second to 28,000 frames a second.
That was a big jump.
Okay, so we're pretty much done with the water bottle.
Okay.
I'd like to take a photo of
Fix
this. So
anything, like
as you can
duct
see,
tape.
we can only see the light itself. We cannot see the bottle and the label on it.
Yeah.
So if finally in the movie, we may want to overlap both the bottle itself and the light.
So you like composite a real picture.
Yeah,
and then-
yeah.
So you just take a photo on your phone and you can do that?
Yeah, you can just use a software to overlap these two things.
Neat.
You're in the photograph. Just photobombing the bottle.
That sucks.
Okay, let's watch back our bottle.
Yeah, I think they talk about how much space it takes to store 1 second. Dance, you know I'm not touching that, buddy.
This took 8 hours to process, during which time I grew a slightly longer beard.
8
I had a haircut
hours.
as well.
All right, here we go.
Right, okay, so what we're seeing here is the
Whoa.
bottles that's been comped in, basically.
Yeah, so this camera only detects the light itself,
Not bad
which
work.
is like a bluish laser light, which is why you don't really see anything else other than the light looking like that. And then we
So 2,000 picoseconds, so not a lot.
comp in the picture of the bottle.
In the room with my actual eye, it looked like it was constantly lit up, but here we're able to follow the light moving through the bottle. It may not look like it, but this is actually real.
It's refracting the photons, that's why you can see it. But when it's just going through the air, there's nothing to actually reflect the light. so
Yeah,
you
it's
can't see
only
it.
showing up in the bottle. It is interesting. It almost looks like a sort of an 80s film effect,
It does, doesn't it? It looks like...
like some sort of ghost flying into the room.
But actually that...
That's what I imagine greedy sounds like. Ball.
is light.
No, wait, look at this scale. So every frame seems to be 10 picoseconds. And we're just sort of casually watching this light go left to right through the bottle, but in reality, the light is moving 1,000,000 times faster than a bullet. A mental subject.
Yeah.
Okay, so we've shot light through milk. Next experiment?
I agree.
Yep. All right.
For these experiments, we designed a special cavity. We call it chaotic cavity. So when light comes in the cavity, they bounce back and forth multiple times by the mirrors surrounding in the cavity.
You're almost trapping light inside
Yeah,
of
yeah,
the
exactly, exactly.
What's the purpose of this?
This egg
so,
thing.
So this is to create a water vapor surrounding the environment so that light scatters out. The same thing like water
Oh,
ball.
so you can sort of see it
See
a little
it.
bit.
Makes sense.
Yeah. So this is how the system works. Turn on.
Right, let's go do the experiment. How long did it take you to learn?
Okay. I never had enough tissues left over. Impish. Okay.
Use this?
It's maybe a few months to get
A
used.
few months to get used to it.
Yeah, because it's really complicated system.
Yeah, it's really complicated, is it? I hadn't noticed.
Yeah, we're pretty much down.
Okay, so this is the chaotic cavity at 100 billion frames a second. Just like nothing. Once again,
Okay, so we have a singer and a dancer. Seriously? Damn it. Give me a second for anybody who's on Rumble or we should be back up. It's a copyright, so give it a second. It will be back up in like 3 minutes. Sorry, y'all. Pausing and commentating, fair use. Exactly, Aaron. Like, I don't know. I assume nobody can hear me yet, but it should be back up. If you're on Rumble, we're waiting for YouTube to come back up. Come on. Come on, come on, come on. I mean, if that's not fair use, man, I don't know what it is. Like, you can't, nothing's fair use if okay, we're back up. Nothing's fair use if you can't use fairly use content. Like, that's insane. Like, maybe I should put me on there. I didn't have me on there for a minute. Maybe that's part of it. So we'll see if that helps. But that's insane. It's fair use. We're using it for educational purposes.
frames a second.
Let's keep
Just
going.
like nothing.
See how
Once
many
again,
more times.
The duration of this video is...
So this is sorry, I'm all flustered now. So this is a particle of light being, like they said, being trapped. Yeah, I think it's the AI too. This is a particle of light being trapped and bouncing around those mirrors setup that they show. So it looks like it's more of a particle than a wave to me, but
You can't even get your head around how short amount of time it is. That's
yeah,
amazing.
it's ridiculous.
When we were in the room, it looked like the whole thing was glowing, but now we can see the individual pulse of light bouncing around this thing. Looks like a weird version of Pong.
And this is 1 femtosecond of laser pulse. So as if he just went like with the laser.
And I'm sure y'all come back, but and maybe some of you went over to Rumble, but oh, what's up, Dance? Yeah, if you want to stay over here, that's cool too. You missed the start of the stream. So we're discussing wave theory. Wave theory is the topic today. So we went into some of the key players, Planck, Huygens and Isaac Newton, and we didn't get very far in. We got into, is it a particle or a wave, that debate, and so that's where we're at.
A femtosecond pulse.
Yeah.
And if you pause it, you can see it's like a dot of light.
And they've like comped in the shape of the mirrors.
Yeah.
I wonder
Like
if
I
you
said,
could
it was-
actually build like a
It
big
was
maze
completely lit up
to
the
get it
entire
around.
time.
Like you could do like a little
So-
maze and try and get to the end.
World's fastest maze completion.
Yeah.
Light.
Oh, I almost went in the corner there.
It is. It's like the DVD
yeah.
screensaver, isn't it?
Yeah,
You just
no
want it
worries.
to go straight in the corner.
It's nearly. So this one's 100 billion.
Yeah.
Should we see
I
what
should
500
replace that.
billion looks like?
For Hayden's thing.
All right, so the area is quite small. So
Yes.
There's no way that we can stand in and be filmed by this camera. But
So-
alternative solution, little mini figurines of us.
Wait, why is mine? Oh, for goodness sake!
All right?
Again,
So
every
we'll put them-
time.
Put them on there.
Flipping heck.
All right.
So you'll see it propagate
So
up.
in this experiment,
person.
instead of shooting light from the side,
Yeah.
I changed the beam path to bounce back this mirror, and use a concave lens to expand the beam to shoot at the angle.
So this is more about scattering light on the surface.
So this is more about trying to make that light scatter up the figurine instead of just a direct pong bounce or diffraction through the water bottle.
Of the
Yes.
figurines.
You're sweeping across the surface of
Okay.
the figures.
Because we're obviously not see-through, so.
Yeah. Yeah. So this is the static image of the two figures. Now I'm doing 500 billion frames per second with
500.
2x2 coding.
So 2x2 on a.
Seriously, I'm down again. Oh, YouTube. I don't understand how we're supposed to. So I don't get it, guys. Does anybody, Jude, I know you hate going over to Rumble, but does anybody have an issue? Oh, you can't hear me anyways because you're over here. Let's see if it's back up yet. Nope, not yet. Not yet, not yet, not yet. This is going to be a fun one on the back end, too. Trying to fight this. Yeah, AP, there's no such thing as fair use anymore. I believe we're back up on YouTube. Guys, I'm gonna go over to Rumble exclusively. I sincerely apologize, Jude, but they're just gonna keep knocking it down, and we can't talk about it over here, and it's gonna get really annoying. So, I apologize, but I am going to end the YouTube stream for no other reason than to build my footprint on Rumble. I apologize in advance. Hopefully see you guys all over there. I am killing YouTube now.